Foundation models, the technological foundation of modern artificial intelligence. Artificial intelligence is often encountered through visible applications: conversational assistants, image generators, coding tools, scientific platforms, and enterprise copilots. Beneath many of these applications, however, lies a common technological layer. That layer is the foundation model. Foundation models have changed the way artificial intelligence is developed. Instead of building a completely separate model for every task, developers can begin with a broadly trained model and adapt it for many different purposes. In this lesson, we will examine what foundation models are, how they emerged, why they matter, and how they support the wider ecosystem of modern artificial intelligence. This is the fourth paper in the AI Foundation series. The first paper introduced the fundamental concepts of artificial intelligence. The second examined how AI is being applied across industries. The third explored human-AI collaboration and the principles of responsible AI. We now turn to the technological layer that makes many contemporary AI capabilities possible. Foundation models. This paper provides an important bridge in the series. It connects our general understanding of artificial intelligence with the subjects that follow: generative AI and AI agents and intelligent systems. Foundation models underpin many of the systems that generate language, images, code, audio, and video. They also provide reasoning and language capabilities within copilots, enterprise applications, scientific systems, and emerging AI agents. Understanding foundation models therefore helps us understand how the different parts of the modern AI ecosystem fit together. Understanding foundation models. We begin with a fundamental change in the way artificial intelligence systems are designed. Earlier machine learning systems were usually created for one narrowly defined purpose. A model trained to detect fraud was not expected to classify medical images. A forecasting model could not automatically become a writing assistant. Each task generally required its own data, training process, and technical architecture. Foundation models introduced a different approach. They created a reusable layer of machine intelligence that could be adapted across many tasks and applications. This marked a shift from task-specific models to reusable intelligence. A foundation model is a large, pre-trained artificial intelligence model that learns from broad and diverse forms of data. Depending on its design, the training data may include language, images, software code, audio, video, structured information, or scientific data. During this training process, the model learns patterns, relationships, structures, and contextual associations across the data. It does not begin as a finished business application or scientific tool. Instead, it develops broad capabilities that can later be adapted for particular purposes. The same underlying model might support writing, summarization, translation, coding, analysis, question answering, or the interpretation of images and documents. This ability to reuse and adapt a pre-trained model is one of the defining features of the foundation model approach. Rather than beginning every AI project from the ground up, an organization can begin with an existing foundation and customize it for its own needs. This represents a fundamental shift in artificial intelligence development. In the traditional machine learning approach, a team would normally begin with a specific task. It would gather a suitable dataset, train a model for that task, evaluate it, and deploy it for a relatively narrow purpose. A fraud detection model, a demand forecasting model, and an image classification model would usually be developed as separate systems. Foundation models reverse much of this logic. They are trained first on very broad datasets. The resulting model can then be adapted for many downstream applications. The contrast is straightforward. Traditional machine learning often means one dataset, one model, and one task. The foundation model approach means broad data, one reusable model, and many possible applications. This does not eliminate the need for specialized development. It changes where that specialization occurs. Instead of training every model from the beginning, developers adapt a common pre-trained foundation. The word foundation was chosen deliberately. A foundation model provides a common technological base upon which many specialized AI systems can be constructed. That base may support conversational assistants, enterprise copilots, scientific applications, healthcare systems, analytical tools, or AI agents. But the foundation is not the completed system. A general model normally requires further adaptation before it can perform reliably in a specific organization or professional setting. It may need access to current or proprietary knowledge. It may need to be connected to databases, search systems, calculators, software applications, or other tools. It may require safeguards, access controls, monitoring, and governance. Most importantly, it may require human expertise and approval. The model supplies reusable capabilities. The surrounding system supplies context, knowledge, control, and practical purpose. This distinction is essential. A powerful model is an important component, but useful and responsible artificial intelligence depends on the complete system built around it. The foundation model paradigm produces two important consequences: emergence and homogenization. Emergence refers to the appearance of capabilities that were not individually programmed into the model. As models become larger and are trained on broader data, they may become able to perform unfamiliar tasks from instructions or a small number of examples. They may show improved language generation, coding assistance, cross-modal interpretation, or other capabilities that become visible only at sufficient scale. This creates considerable opportunity. A single model may acquire capabilities that can be reused across many applications. The second consequence is homogenization. When one underlying model supports many different applications, development becomes faster and more economical. Organizations can reuse common infrastructure rather than creating every system independently. But reuse also concentrates risk. If the underlying model contains biases, security weaknesses, factual limitations, or other defects, those weaknesses may be inherited by many downstream applications. Foundation models therefore create both economies of scale and shared exposure. Their value comes from broad reuse. Their risks can also spread through that same pattern of reuse. This is why the development of foundation models cannot be treated as a purely technical exercise. It also requires careful attention to reliability, governance, accountability, and human oversight. Having established what foundation models are, and why they represent a different approach to AI development, we can now examine how they evolved from language models into generative, multimodal, and increasingly intelligent systems. To understand why foundation models matter, we must begin with a fundamental change in the way artificial intelligence systems are designed. Earlier, machine learning systems were usually created for one narrowly defined purpose. A model trained to detect financial fraud was not expected to classify medical images. A forecasting model could not automatically become a writing assistant. Each task generally required its own dataset, training process, technical architecture, and evaluation system. Foundation models introduced a different approach. Instead of building every intelligent application separately, researchers developed large models that could acquire broad capabilities and then be adapted for many different purposes. This marked a shift from task-specific models to reusable intelligence. It changed artificial intelligence from a collection of isolated systems into a technological platform upon which many applications could be built. A foundation model is a large, pre-trained artificial intelligence model that learns from broad and diverse forms of data. Depending on its design, the training data may include language, images, software code, audio, video, scientific information, or structured records. During training, the model learns patterns, relationships, structures, and contextual associations across this data. It does not begin as a completed business application, scientific instrument, or professional assistant. Instead, it develops general capabilities that can later be adapted for particular tasks. The same underlying model may support writing, summarization, translation, coding, analysis, classification, question answering, or the interpretation of images and documents. This ability to reuse and adapt a pre-trained model is one of the defining features of the foundation model approach. Organizations no longer need to begin every artificial intelligence project from the ground up. They can start with a broadly capable model and customize it for their own objectives, data, users, and operating environment. This represents a fundamental shift in artificial intelligence development. In the traditional machine learning approach, a team would normally begin with a specific task. It would collect a suitable dataset, train a dedicated model, evaluate its performance, and deploy it for a relatively narrow purpose. Fraud detection, demand forecasting, and image classification would usually require 3 separate datasets and 3 separately trained models. The foundation model approach reverses much of this logic. The model is first trained on very large and diverse datasets. Once this broad pre-training is complete, the same model can be adapted for many downstream applications. The contrast can be expressed simply. Traditional machine learning often means one dataset, one model, and one task. The foundation model approach means broad data, one reusable model, and many possible applications. This does not eliminate specialization. It changes where specialization takes place. Instead of training every model from the beginning, developers adapt a common pre-trained foundation through prompting, fine-tuning, retrieval, tools, or the integration of domain-specific knowledge. The word foundation was chosen deliberately. A foundation model provides a common technological base upon which many specialized artificial intelligence systems can be constructed. That base may support conversational assistants, enterprise copilots, scientific applications, healthcare systems, analytical platforms, or intelligent agents. But the foundation is not the finished system. A general-purpose model normally requires further adaptation before it can perform reliably within a specific organization or professional environment. It may need access to current information or proprietary knowledge. It may need to be connected to databases, search systems, calculators, software applications, or operational tools. It may also require safeguards, access controls, monitoring, and governance. Most importantly, it may require human expertise, review, and approval. The model supplies reusable capabilities. The surrounding system supplies context, knowledge, control, and practical purpose. This distinction is essential. A powerful model is an important component, but useful and responsible artificial intelligence depends on the complete system built around it. The foundation model paradigm produces 2 important consequences: emergence and homogenization. Emergence refers to the appearance of capabilities that were not individually programmed into the model. As models become larger and are trained on broader data, they may become capable of performing unfamiliar tasks from instructions or a small number of examples. They may demonstrate improved language generation, coding assistance, reasoning-like behavior, or the ability to work across several forms of information. These capabilities may become visible only when the model reaches sufficient scale. Emergence creates considerable opportunity. A single model may acquire capabilities that can be transferred and reused across many applications. The second consequence is homogenization. When one underlying model supports many different applications, development can become faster, less expensive, and more scalable. Organizations can reuse common infrastructure rather than constructing every intelligent system independently. But widespread reuse also concentrates risk. If the underlying model contains biases, security weaknesses, factual limitations, or design defects, those weaknesses may be inherited by many downstream applications. Foundation models therefore create both economies of scale and shared exposure. Their benefits can spread widely through reuse, their weaknesses can spread through the same mechanism. This is why foundation models cannot be treated as purely technical products. Their development and deployment also require careful attention to reliability, security, governance, accountability, and human oversight. Having established what foundation models are and why they represent a different approach to artificial intelligence, we can now examine how they evolved from language models into generative, multimodal, and increasingly intelligent systems. The evolution of foundation models has not followed a single path. It has involved a series of connected developments: larger language models, generative systems, multimodal models, domain-specific platforms, distributed approaches, and increasingly intelligent systems capable of using tools and coordinating actions. The earliest stages of this progression focused mainly on improving the ability of models to process and generate language. Over time, however, the foundation model concept expanded far beyond text. Models began to work with images, audio, video, scientific information, biological sequences, satellite imagery, industrial data, and other forms of structured and unstructured information. At the same time, foundation models began to move beyond producing isolated outputs. They increasingly became components of larger systems incorporating knowledge, tools, workflows, memory, and human oversight. The result has been a progression from language models toward generative, multimodal, and increasingly intelligent systems. Several developments drove this transformation. The first was the growth of transformer architectures. Transformers made it possible to process large sequences of information while identifying relationships between elements that may be widely separated within the data. The second was the availability of much larger training data sets. Models were exposed to enormous collections of text, images, software code, audio, and other information. The third was a dramatic increase in computing power. Advanced processors, large data centers, distributed computing, and improved training infrastructure allowed researchers to develop models of unprecedented scale. But scale alone was not sufficient. Progress also depended on better optimization methods, instruction tuning, reinforcement learning from human feedback, and more effective approaches to prompting and adaptation. Longer context windows allowed models to consider more information at one time. This improved their ability to work with extended documents, complex conversations, and multi-stage tasks. Together, these developments transformed language models from systems requiring extensive task-specific training into increasingly general-purpose models capable of responding to instructions and examples. One of the most significant consequences of this progression was that natural language became a general-purpose interface for artificial intelligence. Earlier software systems required people to learn commands, menus, programming languages, or specialized operating procedures. Foundation models introduced a different form of interaction. A person could describe the required task in ordinary language. The same interface could be used to request a summary, write a document, translate a passage, classify information, analyze data, generate software code, or explore a complex question. This changed the relationship between people and artificial intelligence. Instead of programming every task explicitly, users could increasingly describe the objective, provide relevant context, and offer examples of the desired result. Natural language therefore became more than a communication tool, it became a flexible method for directing computation. This development also made advanced artificial intelligence capabilities available to many people who did not have specialist training in programming or machine learning. However, the apparent simplicity of the interface should not obscure the complexity of the system beneath it. The quality of the output still depends on the model, the information provided, the design of the surrounding system, and the judgment of the person using it. The next major stage was the rise of generative foundation models. Earlier, artificial intelligence systems were often designed primarily to classify information, identify patterns, make predictions, or recommend actions. Generative models expanded the role of artificial intelligence from interpretation to creation. A single foundation model could now generate written text, software code, images, audio, music, video, molecular structures, protein sequences, and synthetic data. This represented more than an additional AI capability. It changed the economic and operational role of the model. The same underlying system could support writing, research, design, communication, programming, analysis, and many other forms of knowledge work. Generative capability also made foundation models more visible to the public. People could interact with them conversationally and receive outputs that appeared coherent, creative, and highly responsive. But generation introduced important risks. A model could produce information that sounded convincing but was inaccurate. It could reproduce bias, create misleading content, or generate material that raised questions of ownership and intellectual property. The capacity to generate content therefore increased both the usefulness of foundation models and the importance of verification, safeguards, and human review. Foundation models then progressed from working mainly within one type of data toward integrating several forms of information. A language model processes text. A computer vision model analyzes images. A speech model works with audio. Multimodal foundation models attempt to bring these capabilities together. They may process or generate text, documents, images, charts, audio, speech, video, sensor information, biological sequences, and spatial data. This matters because most professional and scientific work is not confined to plain text. A doctor may need to consider medical images, clinical records, laboratory results, and genomic information. An engineer may work with diagrams, sensor readings, technical documents, and video from an industrial site. An environmental scientist may combine satellite images, maps, field observations, weather information, and statistical models. A multimodal system can potentially examine relationships across these different forms of information. The progression has moved from specialized visual models to text-to-image systems, to vision language models, and then toward more unified assistants capable of understanding and generating several kinds of content. Multimodality therefore brings artificial intelligence closer to the way real-world problems are represented, through combinations of language, images, measurements, records, and observations. The overall direction of progress can be understood across several parallel dimensions. Foundation models are moving from narrow specialization toward broader and more reusable capabilities. Learning is shifting from heavy dependence on labeled examples toward self-supervised methods that can learn from enormous quantities of largely unlabeled data. Models are moving from a single mode of information toward multimodal systems. General-purpose models are being complemented by domain-specific models designed for areas such as healthcare, biology, geospatial analysis, manufacturing, and cloud operations. Centralized development is also being supplemented by distributed and federated approaches in which organizations may collaborate without transferring all their sensitive data to one location. At the same time, artificial intelligence is moving from static outputs toward action. Models are increasingly connected to tools, applications, workflows, and agents capable of carrying out authorized tasks. Perhaps most importantly, attention is beginning to move beyond model size. A larger model is not automatically a better system. Data quality, reliability, efficiency, adaptation, transparency, security, evaluation, governance, and fitness for a particular purpose are becoming equally important measures of progress. Foundation models are therefore not evolving merely by becoming larger. They are becoming more general, more multimodal, more specialized where necessary, more connected to external systems, and more closely integrated into practical human activity. To understand how these capabilities are created and customized, we must now examine the two central stages of foundation model development: pre-training and adaptation. We can now turn from the evolution of foundation models to the processes that make their broad capabilities possible. A foundation model does not become useful through scale alone. Its development involves a sequence of stages in which the model first acquires general capabilities and is then adapted to a particular purpose. The process begins with pre-training. During pre-training, a model learns from extremely large and diverse collections of data. This creates a broad base of patterns and relationships that can later be transferred to new tasks. The pre-trained model is then adapted. It may be guided through instructions, specialized data, external knowledge, software tools, or connections to organizational systems. These two stages perform different functions. Pre-training creates a reusable base of capabilities. Adaptation converts those general capabilities into something useful within a particular task, domain, institution, or operating environment. The distinction helps explain why foundation models can support so many different applications without being trained again from the beginning for every new use. Pre-training is the first and usually the most computationally demanding stage. During this process, a very large neural network learns from enormous quantities of largely unlabeled data. The data may contain trillions of words, billions of images, extensive collections of software code, scientific records, audio, video, or combinations of several types of information. The model is not manually taught every concept contained within this material. Instead, it learns through self-supervised methods. It may be asked to predict a missing word, identify relationships between different parts of an image, complete a sequence, or anticipate the next element in a stream of information. By repeatedly performing such tasks across vast datasets, the model gradually adjusts its internal parameters. It begins to identify patterns in language, visual structures, software syntax, contextual relationships, sequences, and other forms of information. It is important to understand that this learning process is not the same as storing a library of individual documents for later retrieval. The model develops a complex internal representation of statistical patterns and relationships across the training data. This is what allows knowledge acquired during pre-training to be transferred to tasks that were not individually specified in advance. Pre-training therefore produces a broadly capable model, but not necessarily a model that is ready for reliable use in a particular organization. That requires the second stage, adaptation. Adaptation converts a general-purpose foundation model into a system suited to a more specific objective. This may involve fine-tuning the model on specialized examples. It may involve instruction tuning so that the model responds more effectively to human requests. It may also involve prompt engineering, reinforcement learning, or the integration of domain-specific data. An organization could adapt a general foundation model to work with medical literature, financial documents, manufacturing records, legal material, scientific information, or internal business knowledge. The objective is not always to change everything the model has learned. Instead, adaptation builds upon the capabilities acquired during pre-training. This substantially reduces the time, data, computing power, and cost required to develop specialized artificial intelligence applications. Adaptation also makes it possible for several specialized systems to share the same underlying model. A healthcare assistant, a financial analysis tool, and an industrial support system may begin with a common pre-trained foundation. Each can then be adapted using different knowledge, instructions, safeguards, and operating controls. The general model provides transferable capability. The adaptation process gives that capability a particular context and purpose. There are several ways to adapt a foundation model, and different tasks may require different combinations of methods. The simplest method is prompting. Prompting guides the model through natural language instructions without changing its underlying parameters. The user describes the task, supplies relevant context, and states the form of the desired output. Few-shot learning extends this approach by including examples in the prompt. Instead of merely telling the model what to do, the user shows it one or more examples of the required pattern. The model then attempts to infer how the new task should be performed. Fine-tuning goes further. The model is trained on task-specific or domain-specific data so that its internal parameters become better suited to a particular application. Full fine-tuning can produce strong specialization, but it may require substantial computing resources. Parameter-efficient fine-tuning modifies only a small portion of the model or adds relatively small adaptive components. This reduces cost and allows several specialized versions to share the same underlying foundation. Retrieval-Augmented Generation takes a different approach. Instead of relying only on information represented within the model, the system first retrieves relevant material from an external source. The model then uses that material while preparing its response. This can provide access to current, proprietary, or highly specialized knowledge without requiring the complete foundation model to be retrained. These methods are not mutually exclusive. A practical system may combine prompting, examples, fine-tuning, retrieval, and organizational knowledge to achieve the required level of usefulness and reliability. Retrieval is one part of a broader movement toward connecting foundation models to the outside world. A standalone model can generate or classify information, but its knowledge may be incomplete, outdated, or insufficiently specific for the task. Connecting the model to external systems expands what it can do. A search system can provide access to current public information. An enterprise document repository can supply internal policies, reports, procedures, and institutional knowledge. A database can provide structured records. A calculator can perform precise numerical operations. A code interpreter can execute and test software instructions. Business applications can allow the model to interact with customer records, project management platforms, financial systems, or other organizational tools. Operational systems may provide sensor data, performance indicators, or information from physical equipment. These connections can improve relevance, currency, and practical usefulness. They can also reduce some forms of error by allowing the system to retrieve evidence or perform calculations rather than relying entirely on the model's internal representations. However, connecting a model to external tools also creates new responsibilities. Access must be controlled, retrieved information must be trustworthy, sensitive data must be protected, actions must be monitored, and the system must remain within the authority granted to it. Tool augmentation therefore increases both capability and the need for careful system design. This leads to one of the most important developments in modern artificial intelligence, the movement from standalone models to complete AI systems. The foundation model may remain at the center, but it is only one component. A complete system may combine the model with retrieval, enterprise knowledge, memory, databases, software applications, analytical tools, and AI agents. Workflow orchestration may determine the sequence in which tasks are performed. Monitoring systems may evaluate performance, detect errors, and record actions. Governance controls may define who can use the system, which information it can access, and which actions it is permitted to take. Human approval may be required before important recommendations are accepted or consequential actions are executed. This broader architecture addresses a fundamental limitation of foundation models. They are general and incomplete. Their practical value emerges when they are combined with current knowledge, domain expertise, operating rules, external tools, and human judgment. The model contributes language, interpretation, generation, and reasoning-like capabilities. The surrounding system provides evidence, memory, execution, control, accountability, and purpose. The main unit of innovation is therefore shifting. It is no longer only the model, it is increasingly the complete system built around the model. Having examined how foundation models are trained, adapted, and connected to wider systems, we can now explore the different types of foundation models and the domains in which they are being applied. Foundation models are sometimes discussed as though they were simply another name for large language models. That is not the case. Large language models are an important category of foundation model, but the foundation model concept is much broader. Different models are designed to learn from different forms of information. Some focus primarily on language. Others work with images, speech, video, software code, scientific observations, geographical information, or time series data. Multimodal models combine several of these forms within a single system. This expanding family reflects an important development in artificial intelligence. Foundation models are moving beyond the generation of text and into areas where intelligence depends on understanding physical processes, biological structures, visual evidence, operational data, and complex interactions across several sources of information. The same general principle remains constant. A model is pre-trained on broad data, develops reusable representations, and is then adapted to support many downstream tasks. What changes is the nature of the data, the structure of the domain, and the purpose for which the model is used. The main categories include large language models, which are trained primarily on text and support tasks such as writing, summarization, translation, coding, and question answering. Vision models learn from images and may be used for classification, detection, segmentation, or visual interpretation. Vision language models connect visual information with natural language. They can examine an image, answer questions about it, or relate diagrams and photographs to written explanations. Speech and audio models work with spoken language, sound, and acoustic patterns. Video models process sequences of moving images and may support recognition, generation, summarization, or analysis across time. Code models learn patterns from software repositories and programming languages. Scientific foundation models are trained on data representing physical, chemical, biological, or mathematical systems. Geospatial models learn from satellite imagery, maps, and spatial information. Time series foundation models work with data that change over time, including financial indicators, sensor readings, energy demand, weather patterns, and equipment performance. Multimodal models attempt to integrate several of these capabilities. The important point is that large language models represent only one branch of a much wider family. Foundation models increasingly provide reusable intelligence across many different forms of information. As general-purpose models matured, researchers began applying the same approach to specialized fields. This produced the movement from general intelligence toward domain intelligence. A domain foundation model is trained or adapted using information that reflects the underlying structure of a particular field. In healthcare, this may include biomedical publications, clinical records, and medical images. In biology, the data may include DNA, RNA, protein structures, molecular information, gene expression, and single-cell measurements. Geospatial models may learn from multispectral satellite imagery and other forms of Earth observation data. Industrial models may use sensor readings, engineering records, maintenance histories, and operating data. Cloud management models may learn from workloads, configurations, performance indicators, and infrastructure telemetry. The purpose is not simply to teach a general model the vocabulary of a specialist profession. A genuine domain foundation model seeks to learn the relationships, structures, and recurring patterns that define the domain itself. This can make the model more useful for specialized analysis, prediction, interpretation, and decision support. It can also improve efficiency by reducing the amount of labeled data required for every individual task. But domain specialization introduces additional responsibilities. Performance must be evaluated within the actual operating environment. Data quality must be assessed carefully. Professional standards, regulatory requirements, and domain-specific risks must be incorporated into the system. The more consequential the application, the more important expert oversight becomes. Bioinformatics provides one of the clearest examples of the expansion of foundation models into scientific domains. Biological information exists in many different forms. It includes DNA and RNA sequences, proteins, gene expression data, molecular structures, single-cell measurements, biomedical literature, medical images, and biological knowledge graphs. These datasets are vast, complex, and often difficult to label. In many areas of biology, obtaining expert annotations is expensive, time-consuming, or technically challenging. Foundation models offer a possible solution. By pre-training on large quantities of unlabeled biological information, a model can learn reusable representations before it is adapted to a particular scientific task. Biomedical language models, for example, learn from research papers and clinical text. Protein language models treat sequences of amino acids in a manner somewhat similar to language. They learn patterns associated with protein structure, function, interactions, and sequence generation. Genomic foundation models learn from DNA sequences and patterns of genomic regulation. RNA models examine sequence, evolutionary, structural, and functional relationships. Single-cell foundation models learn from large collections of cellular data. They may support cell classification, perturbation prediction, gene network analysis, and the integration of several forms of biological measurement. The field is also becoming multimodal. Researchers are increasingly combining biological sequences, molecular structures, medical images, scientific literature, and clinical records within integrated systems. This progression moves artificial intelligence from processing biological text toward representing biological systems themselves. The potential applications are substantial, but scientific validation remains essential. Biological plausibility, reproducibility, experimental confirmation, and expert interpretation cannot be replaced by model output alone. Healthcare and medical imaging represent another important area of development. Traditional medical artificial intelligence has often relied on narrowly trained models. One model might classify a particular type of scan, another might detect a specific disease, a third might perform image segmentation or estimate patient risk. Each model may be limited to a particular imaging system, population, institution, or clinical question. Foundation models offer a different possibility. A model can be pre-trained on broad collections of medical data and then adapted across several diagnostic and analytical tasks. Potential applications include medical image classification, disease detection, segmentation, clinical question answering, report generation, risk estimation, drug discovery, and treatment planning. Multimodal healthcare systems may combine images, clinical notes, laboratory results, genomics, and other patient information. This could allow the model to consider a broader clinical context than a narrowly trained image classifier. However, healthcare also illustrates the limits of transferring a model from one environment to another. Hospitals use different equipment, procedures, record systems, and patient populations. A model that performs well in one institution may not perform equally well elsewhere. Clinical deployment therefore requires careful validation, privacy protection, interpretability, monitoring, and professional accountability. The clinician must remain visibly and substantively in control. Foundation models may assist with analysis, documentation, and decision support, but responsibility for clinical judgment cannot simply be transferred to the model. The foundation model paradigm is also extending into scientific and geospatial analysis. Large quantities of observational data are available from satellites, remote sensing instruments, field surveys, and environmental monitoring systems. These data contain information about land, water, forests, agriculture, settlements, weather events, and changes in natural systems. Geospatial foundation models can be pre-trained on satellite imagery and adapted to several Earth observation tasks. They may support flood mapping, wildfire analysis, crop classification, land cover mapping, reconstruction of areas obscured by cloud, and long-term environmental monitoring. This approach can reduce dependence on large labeled datasets for every new geographical task. A pre-trained model may already have learned general patterns associated with terrain, vegetation, water, seasonal change, and human infrastructure. It can then be adapted for a particular region or application. The significance of this development extends beyond image recognition. These models are learning representations of natural systems, spatial relationships, and environmental processes. They may support disaster preparedness, agricultural planning, ecosystem monitoring, climate analysis, and natural resource management. But geospatial applications also face domain shift problems. Landscapes, climates, crops, sensors, and observation conditions vary greatly across regions. Local knowledge and ground-based validation therefore remain necessary. The model can help interpret the Earth from above, but meaningful decisions still require an understanding of conditions on the ground. Foundation models are also moving from content-oriented applications into industrial and operational systems. In manufacturing and process industries, potential uses include process monitoring, fault diagnosis, predictive maintenance, production optimization, digital twins, equipment control, and operator decision support. These environments differ substantially from internet-scale language applications. Industrial models must work with sensor readings, time series data, engineering constraints, physical processes, plant-specific conditions, and strict safety requirements. An incorrect answer in a conversational application may be inconvenient. An incorrect recommendation in an industrial control environment may damage equipment, disrupt production, or create a safety risk. Industrial foundation models must therefore be closely integrated with operating rules, validated data, monitoring systems, and human authority. The same progression is appearing in cloud and information technology operations. Cloud management models may learn from workloads, configurations, performance metrics, and infrastructure environments. They can then be adapted for workload scaling, performance optimization, incident prediction, capacity management, and artificial intelligence operations, commonly known as AI ops. These applications demonstrate a wider shift. Foundation models are no longer concerned only with interpreting or generating information. They are increasingly being developed to support real-time operational decisions across digital and physical systems. Across bioinformatics, healthcare, geospatial analysis, industry, and cloud operations, the pattern is similar. Broad pre-training creates reusable capabilities. Domain adaptation makes those capabilities relevant to a particular field. Tools and operational systems convert analysis into practical support. Human expertise, validation, and governance determine whether the result can be trusted. Having examined the expanding range of foundation models and their applications, we can now consider the benefits they offer, the risks they introduce, and the governance required for their responsible deployment. The expansion of foundation models across language, science, healthcare, industry, and enterprise computing demonstrates their considerable potential. But capability alone does not determine whether an artificial intelligence system is valuable. Foundation models create important advantages. They can reduce the time and cost required to develop new applications, support the reuse of common infrastructure, and make advanced artificial intelligence available to a wider range of organizations. At the same time, they introduce significant technical, economic, legal, environmental, and institutional risks. The same model may support many applications. This creates efficiency, but it also means that weaknesses in the underlying model can affect numerous downstream systems. Responsible deployment therefore requires a balanced view. Organizations must examine not only what a foundation model can do, but also how reliably it performs, what data it uses, which systems it can access, who remains accountable, and how its outputs and actions are governed. The central question is not whether foundation models are powerful. It is whether that power can be applied safely, transparently, efficiently, and under meaningful human control. One of the main advantages of foundation models is that they change the economics of artificial intelligence development. In the traditional approach, an organization may need to gather a new dataset, train a new model, and build a separate technical system for every application. Foundation models provide a reusable starting point. A pre-trained model can be adapted for several tasks without repeating the entire training process. This can shorten development cycles and reduce the computing resources, data requirements, and specialist effort needed for each new application. Foundation models can also reduce dependence on labeled data. Producing high-quality labels often requires substantial time and professional expertise. In fields such as medicine, biology, law, engineering, and finance, the cost of annotation can be especially high. Because foundation models learn broad representations during pre-training, they may be adapted using smaller quantities of task-specific information. Another advantage is scalability. The same underlying model can support writing assistants, analytical tools, customer service systems, coding applications, scientific platforms, enterprise copilots, and intelligent agents. Organizations can reuse technical infrastructure while adapting the model to different departments, users, and operating needs. Transfer learning is central to this benefit. Knowledge acquired during pre-training can be applied to tasks the model was not originally trained to perform. Developers do not have to begin with an empty system every time a new requirement appears. Foundation models also provide the base for multimodal artificial intelligence. A model may work across language, images, documents, audio, video, and structured data. This allows systems to engage with information in forms that more closely reflect real professional environments. These advantages can accelerate enterprise adoption. Organizations that could not afford to build advanced models from the beginning may instead use existing foundation models and concentrate their effort on adaptation, integration, and governance. But these benefits should not be interpreted as automatic. Lower development cost does not necessarily mean low total cost. Faster deployment does not guarantee reliable deployment. A reusable model still requires suitable data, evaluation, safeguards, professional oversight, and integration with the surrounding system. The real advantage of a foundation model lies in its capacity to provide a common base. The quality of the final application depends on what is built upon that base. Despite their capabilities, important technical limitations remain. The first concern is the quality and provenance of the training data. Foundation models may learn from material that is incomplete, duplicated, outdated, biased, copyrighted, or poorly documented. Because the model learns patterns from this data, weaknesses in the source material can become weaknesses in the model. Bias is one example, and if particular populations, languages, regions, or viewpoints are poorly represented, the model may perform unevenly across different groups and contexts. It may also reproduce historical prejudices or associations embedded within the data. A second limitation is hallucination. A foundation model may produce a statement that is grammatically fluent and highly convincing, but factually incorrect. The model is generating an output from learned patterns. It is not automatically verifying every claim against an authoritative source. This makes human review and external evidence particularly important in research, medicine, law, finance, policy, and other high-consequence fields. Models may also produce inconsistent outputs. A small change in the wording of a prompt may lead to a different answer. A response that appears strong in one setting may become unreliable when the context changes. Interpretability remains another challenge. Researchers can examine model architecture, data, training methods, and observed behavior, but they still lack a complete explanation of why very large models develop particular capabilities or fail in particular ways. Evaluation is also difficult. Traditional benchmarks may measure performance on a limited set of questions, but they may not adequately assess robustness, fairness, security, environmental impact, or usefulness in real operating conditions. Domain shift creates a further problem. A model trained in one environment may perform poorly when deployed in another institution, population, geography, language, or technical setting. A healthcare model developed using data from one group of hospitals may not perform equally well elsewhere. An industrial model trained on one type of equipment may not transfer safely to another plant. Privacy and security risks are equally significant. Models may expose sensitive information, reveal details from training data, respond to manipulated inputs, or be targeted through prompt injection and other adversarial techniques. When a model is connected to databases, tools, and operational systems, security failures may have consequences beyond an inaccurate answer. These limitations do not mean that foundation models have no value. They mean that reliability must be demonstrated rather than assumed. Testing, monitoring, evidence, access control, human review, and domain-specific validation are necessary parts of the system. The wider costs of foundation models extend beyond their immediate technical limitations. One concern is the concentration of computing power. Training advanced models requires specialized hardware, large computing environments, extensive datasets, substantial capital, and highly skilled technical teams. These requirements concentrate the ability to develop leading models within a relatively small number of corporations, research institutions, and governments. This concentration can influence who controls the infrastructure, who defines the operating standards, and who captures the economic value. Infrastructure costs are also substantial. Although users may interact with a foundation model through a simple conversational interface, the system behind that interface may depend on large data centers, advanced processors, high-speed networks, storage systems, and continuous technical support. Energy consumption is another concern. Both training and deployment require electricity. As the use of foundation models expands, inference across millions of daily requests may become a major part of their environmental footprint. Data centers also use water, particularly for cooling. The environmental cost therefore includes not only electricity, but also water consumption, computing equipment, construction, and the material resources required to maintain large-scale digital infrastructure. Intellectual property questions remain unresolved in many settings. Training data may contain copyrighted material, licensed databases, proprietary code, images, music, or other protected content. Questions arise over whether such material was collected lawfully, how it contributed to the model, and who owns or may commercially use the generated output. Model ownership creates another layer of complexity. A complete AI application may involve a foundation model developer, a cloud provider, a company that adapts the model, an organization supplying proprietary data, a software integrator, and the final user. When an error occurs, responsibility may be difficult to assign. The developer may point to the application designer may point to the underlying model, the organization may point to the user may have had little visibility into how the system was trained or configured. Accountability must therefore be designed across the entire AI supply chain. Governance cannot be added only after deployment. It should define responsibilities, access rights, data controls, evaluation standards, monitoring procedures, escalation mechanisms, and the conditions under which human approval is required. The wider cost of foundation models is therefore not measured only in money or computing power. It also includes environmental resources, legal uncertainty, institutional concentration, and the challenge of assigning responsibility within complex technological systems. The distinction between traditional machine learning and foundation models helps bring these benefits and risks into perspective. Traditional machine learning systems are generally built for a specific task. A foundation model is designed to provide capabilities that can be reused across many tasks. Traditional models often rely on smaller, carefully selected datasets. Foundation models are trained on extremely large and diverse collections of data. Traditional machine learning frequently depends on supervised learning, in which people provide labeled examples. Foundation models rely more heavily on self-supervised learning, allowing them to learn from vast quantities of largely unlabeled information. Traditional models usually offer limited adaptability. When the task changes, a new model may need to be trained. Foundation models are more adaptable. Prompting, fine-tuning, retrieval, or other methods may be sufficient to support a new application. Traditional models generally provide narrow capabilities. Foundation models can acquire broader general-purpose capabilities that transfer across different tasks and domains. These differences explain why foundation models have become so influential. They reduce the need to build every intelligent application from the beginning. They provide the technological base for generative AI, multimodal systems, copilots, assistants, enterprise knowledge platforms, and AI agents. But the comparison also reveals why foundation models require broader governance. A narrow model may create a localized risk. A widely reused foundation model may influence hundreds or thousands of applications. Its strengths can be distributed across an entire ecosystem. Its defects can be distributed just as widely. The foundation model approach therefore brings a different level of responsibility. Organizations must evaluate the underlying model, the adaptation method, the external knowledge sources, the connected tools, and the complete operating system. They must also determine where human judgment remains essential. Foundation models have changed the economics and architecture of artificial intelligence, but their long-term value will depend on more than scale or impressive demonstrations. It will depend on whether they become reliable, efficient, transparent, secure, governable, and suited to the environments in which they are used. This leads us to the future direction of foundation models, systems that are expected to become smaller where appropriate, more specialized, more multimodal, more distributed, and increasingly capable of using tools and coordinating action. The future of foundation models will not be determined simply by making every model larger. The field is beginning to move toward a more varied and practical landscape. Some applications will continue to require very large general-purpose models. Others may be better served by smaller systems designed for a particular domain, organization, device, or operating environment. Future models are expected to combine several forms of information more effectively. They will increasingly work across language, images, audio, video, structured records, scientific measurements, sensors, and spatial data. They will also become more deeply connected to external knowledge, software tools, and operational systems. At the same time, greater capability will increase the importance of control. Models will need to be more transparent, secure, efficient, auditable, and responsive to the requirements of the environments in which they are deployed. This means that the future of foundation models involves several developments occurring together. Models may become smaller where efficiency matters, more specialized where domain expertise is essential, more distributed where data cannot be centralized, and more agentic where systems are expected to plan and act. But these advances will need to remain within clear boundaries of human authority, institutional responsibility, and responsible governance. The next generation of foundation models will therefore be judged not only by what they can do, but also by how reliably, efficiently, and accountably they can do it. Several characteristics are likely to shape this next generation. The first is multimodality. Future systems will increasingly combine language with images, video, audio, documents, tables, sensor readings, scientific information, and other forms of data. This will allow models to work with problems as they actually appear in professional environments, rather than reducing every task to plain text. The second characteristic is greater domain awareness. General-purpose models will continue to play an important role, but healthcare, biology, law, finance, manufacturing, geospatial analysis, and other specialist fields will increasingly develop models adapted to their own data, terminology, standards, and operating conditions. Efficiency will also become more important. Not every task requires the largest available model. Smaller models may provide lower operating costs, faster responses, easier local deployment, and greater privacy. They may be particularly useful when the task is well defined and the operating environment is controlled. Adaptability will remain central. Organizations will need models that can be customized through prompting, fine-tuning, retrieval, adapters, enterprise knowledge, and changing workflows. Future systems are also likely to become more distributed. Data may remain across several institutions, geographical locations, or devices rather than being transferred into one central repository. Models will become more tool-enabled. Instead of relying only on information represented within their parameters, they will retrieve evidence, perform calculations, access software, analyze data, and interact with authorized applications. They will also become more agentic. This means that the model may operate as one component within a system capable of interpreting a goal, planning a sequence of tasks, using tools, assessing intermediate results, and moving work toward completion. Greater context sensitivity will be equally important. A useful system must understand not only the immediate instruction, but also the user's role, the operating environment, relevant policies, available knowledge, and the consequences of different actions. Scientific grounding will become an increasingly important objective, particularly in healthcare, engineering, environmental analysis, and research. Models will need stronger links to evidence, data, validated methods, and domain expertise. Finally, they will need to become more governed and auditable. Organizations must be able to examine which information was used, which tools were accessed, what actions were proposed or taken, and where responsibility lies. These developments illustrate an important change in emphasis. The next generation of foundation models will not be defined by capability alone. Its success will depend on the balance between capability and governance. Federated foundation models represent one possible approach to balancing broad intelligence with local control of sensitive data. Conventional foundation models are generally developed within centralized computing environments. Large quantities of data are collected or made available within a common infrastructure where the model is trained or adapted. This arrangement can be difficult in sectors where information is private, regulated, commercially sensitive, geographically dispersed, or subject to legal restrictions. Hospitals may not be permitted to transfer patient information into a central repository. Banks must protect confidential financial records. Government agencies may hold information that cannot be shared freely. Manufacturers may regard operating data, process knowledge, and equipment performance as valuable commercial assets. federated approaches attempt to address this problem. Instead of moving all raw data to a central location, participating organizations retain their information locally. They may contribute to the development or improvement of a shared model by exchanging model updates, learned parameters, or other controlled information rather than the underlying records themselves. This creates the possibility of shared intelligence without directly pooling all sensitive data. A group of hospitals, for example, might contribute to the improvement of a medical model while continuing to retain patient records within their own systems. Telecommunications providers might collaborate on a model that identifies network problems without transferring complete customer data sets. Manufacturers could learn across several facilities while preserving control over plant-specific operating information. The potential benefits include privacy preservation, access to more diverse data, broader collaboration, and improved performance across distributed environments. But federated foundation models also introduce substantial challenges. Participating organizations may use different systems, data formats, equipment, and operating procedures. Their data may vary greatly in quality and composition. Communication between sites may be expensive or technically difficult. Model updates themselves may reveal sensitive information unless carefully protected. Questions also arise concerning ownership, incentives, accountability, security, and governance. Who owns the shared model? Who decides how it may be used? How are benefits distributed among participants? Who is responsible when the system fails? Federated foundation models are therefore promising, but they are not a simple technical solution. They require trusted institutional arrangements, secure infrastructure, clear responsibilities, and agreed rules for collaboration. Their significance lies in the possibility of developing shared intelligence while allowing organizations to retain meaningful control of their data. Another major direction is the integration of foundation models into AI agents and intelligent workflows. A conventional conversational model usually responds to a prompt with an answer. An agent-enabled system may be expected to do more. It may begin by interpreting a goal. It can then divide that goal into smaller tasks, identify the information required, select appropriate tools, and determine the order in which the work should proceed. The system may retrieve knowledge from documents or databases. It may perform calculations, analyze files, generate code, communicate with software applications, or coordinate several specialized components. It may examine intermediate results and revise its approach when the outcome is incomplete. It may then produce a final document, recommendation, analysis, or operational output. This represents a movement from generating answers towards supporting action. But the term agentic should not be confused with unlimited autonomy. The authority of the system must be defined. An AI agent should not automatically be permitted to access every source of information, use every available tool, or execute every possible action. Permissions must reflect the task, the user's authority, the sensitivity of the data, and the consequences of an error. Human approval becomes particularly important at consequential points. A system may be permitted to prepare a financial analysis but not authorize a payment. It may draft a medical summary but not make an independent clinical decision. It may recommend a change to an industrial process but not implement that change without an authorized operator. A well-designed workflow therefore includes approval gates. The system may interpret, retrieve, analyze, plan, and recommend. A qualified person reviews the evidence, considers the context, and authorizes or rejects the proposed action. Monitoring and audit records are also essential. Organizations must be able to reconstruct what the system did, which information it used, which tools it accessed, and why a particular action occurred. The future of agent-enabled foundation models will therefore depend on the quality of the surrounding architecture. Goals must be clear, tools must be reliable, permissions must be limited, actions must be traceable. Governance must be built into the workflow, and human authority must remain explicit. Foundation models are gradually evolving from systems that produce predictions or content into components of larger intelligent systems, combining knowledge, tools, workflows, domain expertise, and human judgment. The future opportunity is considerable. These systems may help people coordinate complex work, examine large bodies of information, and carry out multi-stage processes more efficiently. But their long-term value will depend on whether greater capability is matched by reliability, security, transparency, accountability, and meaningful human control. We can now bring these ideas together by reviewing the central lessons from the evolution, operation, application, and future direction of foundation models. We can now bring together the central ideas developed throughout this paper. Foundation models represent the reusable intelligence layer beneath much of modern artificial intelligence. Their importance does not arise from a single capability. It comes from the way they combine broad pre-training, transferable knowledge, adaptation, multimodality, external tools, and integration with larger systems. Earlier artificial intelligence models were commonly designed for one narrowly defined purpose. Foundation models introduced a different architecture. A single pre-trained model could provide capabilities that were adapted across many tasks, organizations, and professional domains. This shift changed the economics of artificial intelligence. It reduced the need to build every model from the beginning and allowed organizations to concentrate more of their effort on customization, knowledge integration, workflow design, and governance. Foundation models now support language applications, scientific research, healthcare, biological analysis, geospatial systems, manufacturing, cloud management, generative artificial intelligence, and increasingly intelligent agents. They have therefore become more than a particular type of machine learning model. They form a technological layer upon which much of the modern artificial intelligence ecosystem is being constructed. Several lessons should remain clear. First, foundation models represent a major shift from narrow, task-specific artificial intelligence toward broadly trained and reusable capabilities. The same pre-trained model can support many downstream applications after appropriate adaptation. Second, large language models are only one category within the foundation model family. Other categories include vision models, speech and audio models, code models, scientific models, geospatial models, time series models, and multimodal systems. Third, a foundation model is not a completed application. Its practical value depends on how it is adapted and incorporated into a wider system. Prompting may be sufficient for a relatively simple task. Other uses may require fine-tuning, parameter-efficient adaptation, external knowledge retrieval tools, enterprise data, or specialized safeguards. Fourth, foundation models are becoming increasingly multimodal and domain-specific. They are moving beyond plain text and learning from images, audio, video, scientific measurements, biological sequences, satellite imagery, sensor data, and other forms of information. At the same time, specialist fields are developing models that reflect their own data structures, professional standards, and operating requirements. Fifth, the model is only one component of the complete system. Reliable applications may also require retrieval, memory, databases, software tools, workflow orchestration, monitoring, access controls, governance, and human approval. The quality of the surrounding architecture can be as important as the capability of the underlying model. Finally, reliability, governance, and human oversight remain essential. Foundation models can generate inaccurate information, reproduce bias, expose sensitive data, behave inconsistently, or fail when moved into unfamiliar environments. Their outputs should therefore be evaluated in relation to evidence, context, risk, and the consequences of error. A powerful model may extend human capability. It does not remove the need for human judgment. Foundation models have emerged from decades of progress in neural networks, transfer learning, self-supervised learning, transformer architectures, computing infrastructure, and large-scale data processing. Their development can be viewed as a continuing progression. Artificial intelligence moved from task-specific models to pre-trained models. Pre-trained models developed into large language models. Language models expanded into generative systems capable of producing text, code, images, audio, video, and scientific content. Generative models became increasingly multimodal. Foundation models then moved into specialized fields such as healthcare, biology, geospatial analysis, manufacturing, and cloud operations. Federated approaches began exploring how organizations might develop shared intelligence without centralizing all sensitive data. Agent-enabled systems started connecting models to knowledge, memory, software tools, and multi-stage workflows. The central innovation throughout this progression is not simply increasing model size, it is the creation of a reusable layer of machine intelligence that can be transferred across tasks and embedded within many different systems. This layer may help people examine large bodies of information, generate new content, analyze complex evidence, coordinate workflows, and support decisions. But long-term value will depend on more than technical capability. Foundation models will need to become more reliable. Their outputs must be tested against evidence and professional requirements. They will need to become more efficient. The largest model will not always be the most appropriate model. They will need to become more transparent. Organizations must understand how systems are configured, which information they use, and where their limitations lie. They will need to become more secure. Access to data, tools, and operational systems must be carefully controlled. They will need stronger governance. Responsibilities, permissions, monitoring procedures, and approval requirements must be defined before consequential deployment. And they must remain aligned with human purposes. Artificial intelligence should extend human expertise and support human decision-making rather than obscure responsibility or remove meaningful human control. The future of foundation models will therefore be shaped by a continuing balance. Capability must be balanced with reliability. Efficiency must be balanced with performance. Adaptation must be balanced with validation. Automation must be balanced with accountability. And machine intelligence must remain connected to human knowledge, judgment, values, and authority. Foundation models provide the technological base for the next subject in the AI Foundation series, Generative AI. Generative artificial intelligence refers to systems capable of creating new content, including text, images, software code, audio, music, video, molecular structures, and synthetic data. These visible creative capabilities have attracted widespread public and commercial attention. But generative AI does not exist independently of the foundation model paradigm. Its capabilities emerge from broadly pre-trained models that have learned patterns across enormous collections of information and can generate new outputs in response to instructions, examples, and context. The next paper will examine how these systems create content, how people interact with them, and how they are being applied across professional, scientific, creative, and enterprise environments. It will also examine their limitations. Generated content may appear fluent, convincing, and original while still being inaccurate, biased, misleading, or insufficiently grounded in evidence. Understanding foundation models therefore provides the necessary base for understanding both the possibilities and the risks of generative artificial intelligence. The progression is clear. Foundation models provide reusable capabilities. Generative AI applies those capabilities to the creation of content. AI agents then connect models to knowledge, tools, workflows, and authorized action. Together, these developments are transforming artificial intelligence from isolated predictive models into adaptable systems that can support increasingly complex forms of human work. The next step is to examine generative AI, how foundation models move from learning patterns to creating new content.